combinations and permutations are something that in theory you've talked about before. In practice, it's about hit or miss on if people know what I'm talking about. Combination is the idea of choosing a group of items from a larger group. Where order does not matter. It's the idea of I go to Baskin-Robbins and I want to choose 2 different types of ice cream out of their 32 different flavors. How many different ways can I do that? So that's the kind of idea that's behind combinations. Now combinations have a couple of different notations. These are 3 different notations to reference that you're doing a combination. N combinations of R, C within parentheses, N comma R, or N over R in parentheses. Do not put a fraction bar between them. In combinations, N represents the total number of items that you're working with, while R represents the amount wanted. And the formula for combinations goes N factorial over N minus R factorial, R factorial. Do y'all remember what a factorial is? So before we get to permutations, let's talk factorial. Now the factorial is that exclamation point in a math equation. A factorial is where you multiply by all whole numbers down to the number 1. For example, if I said 5 factorial, that would be 5 times 4 times 3 times 2 times 1. Now, something important you need to know. By definition, 0 factorial is something that will pop up, but 0 factorial, 0 not being a whole number, because whole numbers are technically only numbers above 0. Actually, it's more accurately natural numbers. It is a whole number, but it not being a number bigger than 1 causes issues. 0 factorial is defined to just be the number 1. So if you ever come across 0 factorial, it is equal to 1. So that's what this formula has in it. It's got a bunch of things getting multiplied by numbers smaller than it. We're also going to be talking about permutations today. Permutations are similar to combinations. It's still choosing a group of items from a larger group. But in this case, it is where order does matter. Permutations have some similar notations. They also have a similar formula. There's one fewer notation that you will see though. There is the NPR option, and then there's the P in front of NR. N and R work the same way. N is the total number of items, while R is the amount wanted. This formula, like I said, is very similar to combinations. It is n factorial over n minus r factorial. Combinations and permutations work with one of your favorite things, word problems. They'll work with problems like this. There are 12 horses in a race. How many ways can first, second, and third place finish? So, when it comes to problems like this, first off, do you recognize that you are choosing a group out of a larger group? We're looking at first, second, and third place out of a group of 12. So that's what makes it either a combination or a permutation. Which one depends upon if order matters. If you are running a race, does it matter if you get first, second, or third place? Does it make a difference? Yes, so does order matter? That makes this a permutation. N is the total number of items you're working with. How many total are we working with? 12. R is the number we're choosing. How many places are we choosing? 3. So we are going to do 12 permutations, so P, 3. And I type into my formula, and by type I mean write out. Yes, there is a button for this on your calculator. Yes, on your homework, am I okay with you using it? No, I am not going to show it to you right this second. Yes, I will show you it to you shortly. There's a reason I want to work with the manipulation of the formula. It is going to be one of the big things that we do in stuff that's actually in chapter 10. So I'm just going to work with the manipulation of the formula. Make sure that you are grabbing the right formula. This is permutations, this formula. N factorial, 12 factorial, over N minus R factorial, 12 minus 3 factorial. Now, one thing that you have to know about factorials is factorials do not multiply together nicely. They do not distribute nicely. If you see a factorial on something, that fourth factorial stays on exactly what it's on. Now, this bottom here is on the parentheses 12 minus 3. You cannot distribute the factorial, but you can combine like terms because 12 minus 3 is in parentheses. What is 12 minus 3? No. So I have 12 factorial over 9 factorial. Now, again, can this go into a calculator? Yes. Do I recommend that at least for notes you're following along with what I'm doing without the calculator? Yes. There's a reason for it. 12 factorial, by definition, is 12 times 11 times 10 times. I keep going until I get to what number? 1. Now, I'm going to write till 8, and then I'm just going to write a dot, 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 ending at 1. I could do the same idea with 9 factorial. It's 9 times 8 times 7 times, and I could keep going until I end at 1. Recognizing how permutations and combinations work with fractions is going to be a huge thing when we get into chapter 10 a little bit more. I've got a bunch of stuff multiplied on both top and bottom of a fraction. In other words, I can cross things off of both the top and the bottom because it's all multiplied. This 9 and this 9 will cancel. This 8 and this 8 will cancel. Is there going to be a lot more canceling? All the way down till the 1. The only thing you're going to be left with is 12 times 11 times 10. How many different ways can these horses get first, second, and third place? 12 times 11 times 10 is 1,320 ways. Follow-up question to this. What is the probability that you guessed first and second place correctly? In problems like this, where it's getting to probability, one of the things that tends to help out tends to help by thinking about the problem as filling in slots. We're filling in a first place position, a second place position, and a third place position with this problem. Now, we're looking for the probability that you guess first and second place correctly. To figure this out, I need to figure out how many different ways that I could have correctly guessed first and second place and still had a third place winner. This is where having slots to fill kind of helps out, because you can kind of figure out how many different ways to do for the different things separately. How many different ways can you guess first place correctly? How many horses win first place? 1. How many ways could you have accurately guessed that 1? Not 12. How many of them win? 1. Which means how many ways can you guess that 1 horse? Only 1 way. There's 12 horses to choose from, but only one of them is correct. There is 1 way to choose first place correctly. How many ways can you choose second place correctly? Only one, because there's only one second place winner. It says nothing about choosing third place correctly. So third place comes back to how many different ways can we be left with third place? How many horses are left? 10 horses left. Horses is not spelled like that. For how many places left to fill? 1 place left. So we've got 10 horses left for 1 place. That can be done by its own combination or permutation. Does the order matter which place you get? Yes, we're back to a permutation. How many horses can fill that slot? 10. And how many slots is it? 1. So we're going to do 10 permutations of 1. What are you frustrated about? I don't believe you, but 10 permutations of 1 is 10 factorial over 10 minus 1 factorial. 10 minus 1 factorial is 9 factorial. 10 factorial over 9 factorial is 10 times 9 times 8 times 7 times. I could keep going. What's going to be left? The 10. There are 10 different ways that you can choose first and second place correctly, because there's only one way to choose this correctly. There's only one way to choose this correctly. And one of the things about how you fill in getting this correct and this correct and this correct is you multiply them. By the way, in situations where you're going to choose some things correctly, hint, there's going to be one way to do it. There are 10 ways. I did not leave myself enough space on this problem. There are 10 ways to choose correctly. How do you find the probability of something? If there's 10 ways to do it, and 1,320 ways for just things to happen, probability is calculated by the things that you want divided by total number of ways things can happen. 10 ways will fit what you want. 1,320 ways will fit what you are what can, oh my goodness, are total outcomes. It's outcomes you want divided by total outcomes. Ten divided by 1,320 is a tiny number. You can leave it as a fraction. You do not have to. This is a probability. What do we like probabilities in oftentimes? Decimals or percentages? How do I change a decimal into a percent? Move the decimal place twice, aka multiply it by 100. That being said, you can't just give the answer to me rounded to 4 decimal places. It would be 0.76%. It'd be really low probability. Okay, am I catching that the probability problem threw us off? Okay. Some problems today are going to be probability, some are not. Let's try another problem and then let's see if I can make the probability make more sense on that one. start with a straight problem, and then we'll get to the probability situation. Combination and permutation problems. Do you recognize that we're choosing a smaller group out of a bigger group? That's what makes a combination or permutation. Which one depends on if the order matters. Doesn't matter what order I choose the 4 students in. No, they're not being treated any differently by being chosen first versus being chosen last. They're just one of the 4. If order does not matter, is that a combination or a permutation? Combination. N is the total number. How many do I have to choose from? 24. R is the number I'm wanting to choose. How many am I choosing? 4. So, starting here, it's going to be 24 combinations of 4. Again, I'm going to use the formula to manipulate, and then I will show you where to do it on your calculator. So this is my formula. N factorial, 24 factorial, over N minus R factorial, that's 24 minus 4, in a factorial, times R factorial, that's 4 factorial. You cannot multiply factorials together nicely, but you can simplify the parentheses. In other words, I can make this 24 factorial over 20 factorial, 4 factorial, but I cannot make the denominator 80 factorial. That is not accurate. The expansion of this. I just expand each of them separately. 24 factorial, 24 times 23 times 22 times 21 times 20 times 19, blah, 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 blah. Goes all the way down to 1. (20 factorial, blah, 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 goes all the way down to 1. 4 factorials, 4 times 3 times 2 times 1. What is going to cancel out? I choose the bigger one. The 20 all the way down to the 1 on both top and bottom. Technically, I could simplify this a little bit more before I multiply, but I don't have to. Because I can take a 4 out of both of those, I can take a 3 out of both of those, etc. You don't have to. 24 times 23 times 22 times 21 is this. 4 times 3 times 2 times 1 is 24. There are 10,624 ways I could randomly choose 4 students to go to the desk floor. And here's where the probability comes in. Here's where the tripping point came in. Again, the way that I find easiest to work with is working with filling in slots. How many slots are we filling in? Not 6. Not 2. 4. We're still choosing 4. Four students are going to the next door. Because this is a follow-up to this. These two questions are related. Order does not matter, so I'm just going to choose any 2 of them to be the slots for boys, which means the other 2 are for the girls. Assuming gender is binary, we're not having that conversation. We're just, for math's sake, we assume gender is binary. Okay. Now, in the horses problem, we were filling in first place and second place with the actual winners. There was only one way to fill in first place. There was only one way to fill in second place and be accurate. You had to guess the correct ones. This one's a little bit different, and this one's probably a little bit more similar to what you're going to see. We didn't say anything about specific boys fitting here, specific girls fitting here, which means order does not matter. We just need to choose 2 of them. How many boys do we have to choose from? 6. And since we're filling in multiple slots, we're going to do a combination again. How many are we choosing? 2. So this is going to be 6 combinations of 2. We'll get back to their math in here in a second. I also need to pick a couple of girls then. Because if I want exactly 2 boys, this needs to be filled up with just girls. How many girls are there to choose from? How'd you get 18? There were 24 kids in the class, 6 of them are boys. If we're assuming gender's binary, there's 18 girls. How many am I choosing from? Or how many am I choosing? 2. And since order does not matter, this is 18 combinations of 2. The way that probability works is when you want this and this, you multiply those amounts, and that'll give you the total number of ways you can do things. Now, I mentioned there's calculator buttons, right? Do you know where they are? If you don't, would you like to know? Even the little baby calculators have these buttons. There's my Casio. There's my Casio. Okay. Generally, the first thing you want to do, because I'm just going to type that entire thing into my calculator, is you want to do the first number you're going to type in. So I'm going to start with the 6. Regardless of which calculator I'm on, I'm going to start with typing in a 6. To get to combinations, if you have a TI graphing calculator, click Math. Scroll over to the probability menu. There's NPR, there's NCR, there is factorial. We're doing a combination, so we're going to do the third option. Let's say you've got one of the little baby TIs. Start with my 6. See that PRB button right there? That's a probability menu. Click it. You will see NPR, NCR, and factorial. Casio's, it's a little more hidden. Under Casio's, you have to click Options. It'll bring up a menu along the bottom. We're going to click F6 to scroll over so that we can find our probability menu. There's factorial, NPR, NCR. I'm doing 6 combinations of 2 and multiplying it by 18 combinations of 2. Once you have that, you divide out the ways that you can do the specific situation by the total number of ways you can arrange things. So it's always going to be this divided by that overall total that you had. Is probability going to show up on your homework? Yes. Is probability going to be the main thing that we're focusing on in this chapter? No. In fact, I'm going to tell you right now, the probability problems are not going to show up on the test.
Why are we doing that?
Because it's going to lead us to something else we're going to do. Mainly next chapter, actually. The combinations and permutation stuff, that's going to be important to this chapter, though.